Today we're going to talk about section 6.2. Sorry, my voice is going a little bit. We're going to reiterate some of the indefinite integral stuff with the plus C's, but we're also going to start talking about a new method called substitution. We're going to talk about what happens when we have a chain rule and we need to undo that chain rule. So first off, the family of all antiderivatives of an integral, of an indefinite integral, is going to be this antiderivative plus C. We talked about that back in section 6.1. So just as a refresher, for example 1, the antiderivative of x, we do x squared over 2, and then the antiderivative of negative sine of x would be plus cosine x plus C. And that's it. That's all we have to do. So a couple of properties. Just a reminder, if there's a constant out front of a function, we can pull that constant out front. And we can break up sums and differences into pieces, just like what we did here. We did the integral of this part, and then the integral of this part, and then we combine them. The power rule is the one that we've been doing, where you add 1 to the exponent and then divide by that exponent plus C. Same thing works when you have a negative exponent. The only exception is when we have a negative 1. U to the negative 1 is 1 over u du. And you guys have done a good job on flashcards so far. That's the natural log of u. But I want you to notice it's actually the natural log of absolute value of u plus C. That's because this function is defined when x is less than 1 or when u is less than 1. This one is not. So we have to do the absolute value of that one when we're working backwards. The trig formulas, those are all some flashcards. Would you take a moment to just quiz yourself, see if you can figure all 6 out? Check your work and see how you did. Make sure you check those negative signs as well. And then last but not least, you've got these formulas. E to the u is e to the u plus c. A to the u is a different one. I want to refresh your brain here. When we did the derivative of a to the x, the derivative was a to the x times natural log of a. So when we do the antiderivative, it's just the opposite. Instead of times natural log of a, it's a to the u divided by natural log of a plus c. This last one you don't have to memorize. We will learn how to do this one by hand at some point. So not one you have to actually memorize. All right, so Leibniz came up with his own notation. He's the one that does the f of x notation. Newton was the one who did the du or dy dx notation. So we're talking about, we've got this function x cubed plus 1, and then we've got a u function of x squared. And I want you to notice these 3 functions. They're very different. The first one has f of x and dx. So if I were to plug in my f of x, excuse me, we know how to do that antiderivative. The antiderivative of x cubed is x to the 4th over 4. And the antiderivative of 1 is x. And we can't forget our plus c. Now, part B says, do the function of u with respect to u. Well, my function is x cubed plus 1, but they said to replace the x's with u. So the u is x squared. Sorry about that. So this time it says f of u du. So I'm going to replace the x's with u. So we get u cubed plus 1 du. Now, this is in terms of u. This says with respect to u. So we straight up integrate like we usually would. U to the 4th over 4 plus u plus c. But the problem is that problem said to find the antiderivative in terms of x. So at this point, I've got my function with u's in it. Now I have to replace it with the x squareds. So we get x squared to the 4th over 4 plus x squared plus c, which is x to the 8th over 4 plus x squared plus c. So different answers here. The last one gets a little bit trickier. It says f of u dx. So we get u cubed plus 1, that's f of u, but then it says dx. I can't do the antiderivative of u cubed plus 1 with respect to x. So in this case, I have to replace the u here in order to be able to do the antiderivative. So we know that u is x squared according to the function up here. So x squared cubed, which is the same thing as x to the 6th plus 1 dx. Now I can do this. I've got my function with respect to x. So if I do the antiderivative, we get x to the 7th over 7 plus x plus c. So those letters matter for each one because notice we got a different function for an answer for all three. All right, so now let's talk about how do we use substitution to help us solve some of these integrals. The reason we would use a substitution is to undo a chain rule. We've got a u, or a function inside of another function. That's one way we would use this property. So it says we're going to have a u, which is a function. And to do this substitution, we're going to have to know a du as well, because I need this to be an f of u du. We're going to integrate with respect to u and then replace the u. So here's this first function, sine of x e to the cosine of x. Our one hint that we want to use for substitution, and we're going to kind of keep a little tally going here. The first thing we're looking for is a chain rule. We're looking for a function inside of another function. So this one's pretty obvious that cosine of x is the function on the inside. So we say, all right, let's let the u, or the inside function, be cosine of x. Now I need to know what is the derivative of u with respect to x. Well, the derivative of cosine is negative sine of x. Now, what I want you to see is our goal here is to replace anything that has an x in it with something that has a u in it. Now, we've done this a few times. I'm going to move this dx over. So I've got du equals negative sine of x dx. So look right here, sine of x dx. We almost have a complete match. Sine of x dx, sine of x dx. I'm going to move the negative 1 over. I'm going to divide by negative 1. And now I have a complete replacement. Everything that's a squiggly here is replaced by negative du. And my cosine of x was replaced by u. So now watch how cool this replacement is. My new integral has an e to the u, because cosine of x was u. And then all of this, sine of x dx, gets replaced with negative du. I'm going to put the negative out front and the du out here. Now that is easy to integrate. So the antiderivative here is negative e to the u plus c. The last thing we have to do is replace that u with our substitution. Our u here was cosine of x. So the answer here is negative e to the cosine of x plus c. So take a look at example 4. what function do you see that's inside of another function? So I see this is the inside function. So I'm going to let that be my u. So we'd say u is 5 plus 2x cubed, which means du dx, the derivative of u, is 6x squared. Now I'm going to move my dx over. And I want you to notice, here's the other part I'm trying to replace. I've already replaced all of this with a u. I'm trying to replace this, x squared dx. Well, there it is, but there's one little piece standing in my way. So I'm going to divide by 6 to get rid of that. So I've got 1/6 du equals x squared dx. Now I have the perfect replacement. X squared dx is going to be replaced by 1/6 du. So now I just rewrite my integral with all of my u's, my replacements. I'm going to start with my u, square root of u, and then the x squared dx gets replaced by 1/6 du. Notice I always put the constant out front. It just makes my life a whole lot easier. Now some of you might not think that that looks a whole lot easier, so I'm going to rewrite this one more time as u to the 1/2. Now we can integrate. When we do this u to the 1/2, we have to add 1 to the exponent, so that's going to be to the 3/2. And then we divide by 3/2 plus c. When we divide by 3/2, that's the same thing as multiplying by the reciprocal, so multiplying by 2/3. So we end up with 2/18 or 1/9 u to the 3/2 plus c. The only thing left now is to replace that u, and we come all the way back to here. Our u was 5 plus 2x cubed. So my final answer, 1/9, 5 plus 2x cubed to the 3/2 power plus c. I want to come back up here and write down a couple more places we would use substitution. The second place that you would see this, or in order to find your u, I'm just going to write this out, picking u. You would do the function that's on the inside of a chain rule. Otherwise, you can look for the function raised to the highest power. The other way I like to look at it, if there's a fraction of some sort, it's always the denominator of a fraction. Or just plain and simple, if you're looking at a function, you would look for the one whose function has its own derivative in the integrand. So a function whose derivative also appears in the integrand. So for example, this particular example, sine and cosine, those derivatives are in the same integrand. So you know one of them is going to be the u. All right, so I do have a detailed sheet for you with all of these, but it's going to help us when we get to example 5. We don't have an antiderivative trick for cotangent. So to do this one, we have to rewrite, and we end up getting cosine of 7x over sine of 7x. Now, using those rules that we just wrote down, we would want to use this bottom function as our u. and then du dx. When we do the derivative of this one, we have to remember to do chain rule. Derivative of the inside is 7. Derivative of the outside is cosine of 7x. Some of you will start to just do this step naturally and just put the du over here and the dx over here. Now, we said this part is u, and I want you to notice what we're left with here is cosine of 7x dx. There's my cosine of 7x dx. I have a 7 standing in my way, so I have to divide by 7. So we've got this 1/7 du equals cosine of 7x dx. All right, so now we rewrite our integral. Cosine of 7x dx gets replaced by 1/7 du, and the sine of 7x was my u, so I have 1 over u. Now, 1 over u is one of those special antiderivatives. The antiderivative of 1 over u, we're going to do 1/7 natural log absolute value of u plus c. Now the only thing left is we have to put the u back in. So we get 1/7 natural log of sine of 7x plus c.